Hello everyone, my name is Jiwei Zhao and I am a faculty member at the University of Wisconsin-Madison. I'd like to share some of my recent research on a nuisance-free inference procedure accounting for the unknown missingness in a regularized likelihood framework. This is joint work with my former PhD student Chi Chen, who is a statistician at Novartis Shanghai. So this project is motivated by analyzing data in large electronic health records like the MIMIC3 database. And if we pin down the data analysis into some statistical problems, one of the very basic questions is how to conduct a regression model to achieve the goal of both parameter estimation and uncertainty quantification. However, there are a few challenges in this type of data analysis, and the foremost challenge is missing data. So the very initial motivation of we do this project is when we do some basic data cleaning on the MIMIC3 database, we found although all the variables have missing values, albumin level, which is a very important biomarker, it has around 30% missing data. So this is a very interesting phenomenon. We'd like to understand more about this phenomenon. And on top of missing data, there are a lot of features that one can extract from this large database. So the question is what we can do about the so many features and how we can do the inference problem if we select some of the features. So to be more specific, we try to achieve the following goals. The first one is about the missingness. And we know that the mechanism model of the missingness is largely unknown. So this is the nuisance parameter, nuisance component in most of the statistical data analysis. And also in EHR database, this type of missing data is more like missing not at random, or we call it non-ignorable missingness. And then once the data are non-ignorable missing, the identifiability is a very challenging issue. And for the many feature problem, we'd like to do a feature selection procedure and on top of missing data. And the inference, what our inference here refers to the post-selection inference, again, on top of missing data. So to be more specific, we have two models in this problem, and we assume a very simple linear regression model with the normal error as our the model of interest, where we have parameters alpha, beta, and gamma. And here you can see we decompose the covariate X into two components, where the majority of the covariate we decode as U, and there's just one covariate we decode as Z. Later on, we will give Z a special name. And we also define missing indicator R to represent whether Y is observed or not. We assume X is fully observed. And we assume the gamma 0, which is a coefficient associated with Z, is non-zero. This is to solve the identifiability problem. And for the missingness mechanism model, we assume the R equals 1 can depend on Y and X, but with an arbitrary form, but it cannot depend on Z. In other words, we assume this missingness mechanism model is a function, is an arbitrary function of Y and U, but not involve the effect of Z. So for this type of Z in the literature, people normally call that is a non-response instrument. So the idea of have this type of variable Z is to solve the identifiability issue, where we try to assume, we try to impose a missingness mechanism model assumption at the very flexible version. So there are two similar approaches. One we call the shadow variable approach. The other one is the instrument variable approach. And we will focus on the shadow variable approach. So this slide and the next slide will give you the main idea of how we use the conditional likelihood approach. Basically, we start with the conditional. We start with the likelihood function of V, which includes both Y and U given Z. We only focus on the fully observed data set. It means with Ri equals 1. And it can be written as the right hand side. Here the key is we are interested in the probability of Vi given Zi. However, the left hand side, Vi given Zi and also given Ri equals 1 is something that we can make inference. Their difference is a fraction. The numerator is a function of v, we call SV, and denominator is a function of z, we call gz. The SV is exactly the Mason-Dixon-Mackinac model. So I don't have time to talk about the details, but the basic idea is we start with the left-hand side of the likelihood function on the subjects with Ri equals 1, and we decompose the Vi with rank statistics and order statistics. And we only focus on the term which is red colored highlighted, and that is actually the rank statistic given the order statistics. And after some algebra, and also use this fact, this term, the rank given order, and it can be written as this type of form. And the numerator and denominator, it doesn't have any nuisance components, and it only includes the conditional PDF of V given Z. And also, furthermore, using a computational feasible version, which is a pairwise fashion, this idea is from the Liang and Qin in 2000 paper, and our objective function can be written as in this type of form. It only includes the conditional PDF of yu given z, but some of the terms of yu, z, they come from the same individual, and some of them they come from the different individuals. Like this one, they come from yiz ui, but z is coming from the j's object. Okay, so here, this slide summarizes the likelihood function. So we have this very complicated likelihood, and from this likelihood, we can see there are a few things. The first one, not all of the parameters are estimable, but unfortunately, we have the beta, which is a coefficient associated with u, is estimable. So this beta is our main interest in the remaining of the talk. And we also have a wij term. This wij, it only includes a model of z given u, and we assume the there's no missing data in modeling w, so we assume the hat of wij hat is available and well behaved. So this slide gives how we solve the computational challenge, and actually the trick is we find after some rearrange of the terms, the L set our objective function can be written as a form which is exactly the contribution. The semantic here is contribution of a conventional logistic regression with G, it derived the data as the response, theta as a coefficient, TK, the derived data is a covariate, and also SK multiplies the log of W hat is the offset term in this logistic regression. And also we require this logistic has no intercept term. In other words, after using this kind of trick, although our objective function looks very complicated, it can be solved using any available software packages for logistic regression models. And we need to select some useful or significant variables from this model. So we want to impose a sparsity assumption and using the regularization approach idea to select the significant variables. There are many penalties that we can use, and the one we particularly use is adaptive lasso penalty, and we use the BIC criteria to choose a tuning parameter. So this is the asymptotic theory given some regularity conditions, especially on the asymptotic normality for the model of Z given U. So here I only represent a parametric model for Z given U. We can also build a semi-parametric model or non-parametric model of Z given U. And this is a so-called oracle property. In other words, we can show for the non-zero components, the estimates follow a asymptotic normality representation. And in general, we can also prove the selection consistency. And there's another thing is about the variance estimation. So we follow a data perturbation approach to estimate the variance. Basically, we generate a IID positive random variables, CI, with mean and the variance both equal to 1. And we have this star version of objective function without penalty and with penalty. So this idea is more like a sampling, like a bootstrap or jackknife idea. And we repeat this data perturbation scheme by say m times, and then we can use the m estimates to formalize the confidence intervals for each of the beta j's, theta j's equivalently. And the theory will follow the previous literature. And I don't have time to talk about the simulation, so I'll just use 1 minute to go over the Mimic3 data application. So we use the albumin level as a response Y, and then we use a calcium level, which is highly correlated with the albumin level as a shadow variable Z. And in the results, you can see the proposed method, it will reinforce some of the parameter estimates, like the shadow variable calcium, like the red blood cell count. But for some others, there are some kind of differences. And both of the models, they only select a few variables which achieve the sparsity assumption. And we also have the solution path plot for this data analysis. So to wrap up, we achieve the following goals. We make a least restrictive assumption via a shadow variable to solve the Mason's mechanism model assumption. And we use a regularized conditional likelihood. And this approach is nuisance-free. And also we propose a perturbation-based variance estimation procedure for the variance estimation. And here there are a few more discussions. So our paper includes a lot more details on this project. So I'd like to thank the NSF to support our research, and thank you very much. For any questions, you can email me to this email address. Thank you.